I will now talk about something that is not very much covered by textbooks or the internet. That is scientifically called group velocity thinking, or more practically downstream development. That is the word forecasters sometimes use. And it points to a very important and interesting mechanism in the atmosphere, how different synoptic systems, highs and low, interact with each other. And the story starts in summer 1944, when our hero Carl Gustav Rossby, who has 5 years earlier discovered the planetary waves, then been involved in the war efforts, now has a holiday in California, and he's lying at the beach of La Conchola, a famous oceanography center in Southern California. And doing that, he listens to the waves. And in America, or in England, it's called the seventh waves. But I understand that in Russia you talk about the ninth wave. Anyhow, it is a name for the familiar variation of the intensity of waves. You can hear how some waves are stronger and some waves are weaker. And then there's a typical period of 7 or 8 waves before the maximum and the minimum and the maximum again. And Rossby, who was also a keen oceanographer, knew that this was due to what is called group velocity. And what is now group velocity? Well, one way to understand it is to take 2 combs with slightly different distances between the tags. And here I have simulated the motion of these 2 combs in the upper right. They move with slightly different speeds and they have slightly different wavelength. And that is in scientific language called it's dispersive. The wavelengths, the wave speed is dependent on the wavelengths, on the distance between the tags. Now if you now add these 2, then you get the group velocity. And here you can see that now the maximum wind, the maximum pattern is moving slightly eastward. So you have the group velocity is different to the phase velocity. It's either stationary or it's moving slowly to the east. So the difference between group velocity and phase velocity is an important mechanism. In this case, they are moving in different directions, which might be the case, but they might also move in the same direction, as we will see, but with different speeds. And when it comes to group velocity in ocean waves, and also if you throw a stone in a pond, you will see how the initial splash will spread out as waves. And if you look carefully, you will see that the waves move rapidly out from the splash, but weaken rapidly. And what easily catches your eye is a maximum wave moving more slowly. That is what you easily see. But this maximum waves is taken up by different waves. At every second, the role of the maximum wave is changing from one wave to the other. And this can be understood as the propagation of energy. This is the propagation of pattern. But pattern is something that our eyes create, and it's not a fundamental physical property, but the propagation of energy is of course a fundamental physical property. And it's for ocean waves slower than the phase speed. And Rossby knew that this group velocity can be derived for equations where the phase speed is dependent on the wavelength. And the story is that then he realized that also his own wave equation, this one, the phase speed is proportional to the square of the wavelength. So also his equation is dispersive. The typical phase speed in the atmosphere is about 10 longitude degrees per day. And then he realized that. He thought, aha, there must be a group velocity attached to my wave equation. So he derived in the sand the group velocity. And it is, in its most simple form, has the same structure as the wave equation, but the sign is not minus, it's plus. And it means that the group velocity is larger than the phase velocity, and we know that it's about 30 degrees per day. And Rossby was very excited when he had done that, and he phoned up to the Oceanography Center, and he got in contact with an Austrian-American, Walter Munk, and told him about his exciting discovery, and asked Walter Munk to come down to him at the beach and do it rapidly, because the tide was coming in from the Pacific and would in due course time sweep out all the equations in the water. So Walter Munk came down, and they discussed this group velocity equation in the sand. Now, the problem is, of course, what does this mean physically? And group velocity is propagating influences, or in a more scientific term, energy downstreams. And it did it in contrast to the ocean waves much faster than the phase speeds. And here is now the same diagram as for the ocean waves, but now applied on the atmosphere. So here you have some sort of energy input, and it goes ahead of the wave created here will move eastward, downstream, but dampen. But the energy will move ahead and shape new, create new waves downstream, thanks to the energy input. And this can be understood in this sort of very simple illustration from a paper by Brian Hoskins and his collaborators. As here you have a deepening cyclone. The released kinetic energy does not only go into the storms, the gale force storms in the lower part of the troposphere, but also in the upper troposphere, feeding into the jet streams, and then moving rapidly down, and then affecting in one way or the other the next downstream low pressure center. And depending on in the forecast, if this is correctly forecasted or not, will depend on the success of the forecast of this storm. Too much or too little, too early or too late, and in the wrong direction, it will affect the development of this downstream low. So you have a sort of domino effect of one low affecting the next downstream, and so on and so forth. And this can be seen most clearly when the atmospheric flow is zonal, when you have low pressure systems moving from west to east. And this is a so-called Hormler diagram. And what is on this Hormler diagram is on the x-axis, the longitudes from the Pacific, America, Atlantic, Europe, Asia, and back to the Pacific. And on the y-axis, the dates, in this case, a 10-day period from the 10th of September to the 18th of September 1993. And what is here is the north-south component of the jet wind at 250 hectopascal. So what I have on this Hormler diagram is a north-south wind component of the upper tropospheric flow at 250 hectopascal. And the negative values means northerly winds, and positive values southerly winds. And in this case, they define a trough in the upper tropospheric flow, and the trough is moving eastward by about 10 longitude degrees per day. So this is what the first information from this Hormler diagram. And then you can also see a lot of other troughs moving from west to east with about 10 longitude degrees per day eastward. But this is just a phase speed. But what might have caught your eyes already are the sequences of successive amplifications of how, for example, a wave developing here is then weakening but creates new waves downstream. And the same for other sequences. And it means that what is happening here over eastern Russia, eastern Asia, on the 18th of September, to some degree depends on what happened upstream, far away, over Europe on the 30th, 5 days earlier, and even over America about 10 days earlier. So it means that the energy released in developments here affect what is happening over eastern Russia 5 or 10 days later. And that is one reason why when we make forecasts over a week or so, we must actually take most of the hemisphere into account, because although the individual weather systems move with 10 degrees per day eastward, the influence is the energy moves 3 times faster. So the energy propagation is about 30 degrees, 30 longitude degrees per day. And at the European Center, the Met Office, and some other numerical weather prediction centers, this group velocity thinking is used to trace the origin of bad forecast, insofar that they are a product of bad initial conditions, initial errors, the butterfly effect, spreading and amplifying downstream. And here is one example from that. It's from quite a long time ago. It was one of the first cases I had to work with when I came to the European Center. It's a one-day forecast, and the error, and of course this was done when about a week after the forecast, when we realized that this was a bad forecast. So why was the forecast bad? It was bad over Europe. Now on day one there was a large error over just west of the United States. And that, by the way, was because there was a wrong decoding of the weathership. So that was the reason for this error. But how could this error affect the forecast over Europe? Then 2 days, 1 day later in the forecast, this error has more or less disappeared, but influenced this downstream negative. So now it's the dominating error. So that the energy has gone from this one to this one, amplifying this error. And then on day 3, we have the blue error here, and now it has sort of intensified a positive error. And you can see the first signs of a negative error further downstream. And then on 4 days into the forecast, the dominating error is a positive one over the mid-Atlantic, and a new negative is forming downstream. And on day 5, the new one is more or less more and more taking dominance, and it will be the cause of the major forecast failure over Europe on day 6. So here you have now the major forecast error. It's a far too deep trough over Europe, and also a too amplified reach to the west of the trough. And so this is a D+6 error. And if we follow the initial error, which was in a low pressure system west of the United States, where is now this low pressure system? Yes, it is actually here. So if we had just followed the phase speed, then we would be somewhere here. But the group velocity has moved the energy 3 times faster to the east. So that helped us to find out the 6-day forecast failure was coming from the East Pacific wrongly decoded ship. Here is a case where we had to work in real time. We were going, a colleague and mine were going to Spain. There had been a long period of dry weather. It was a crisis. And the last forecast to the left here shows that on the day, the 29th of January 1993, it would still be high pressure influence from the Atlantic. But then just the day before we went, the forecast changed. And for the 29th of January, a very intense upper level low was forecasted, and it was then drifting into Spain and Portugal and giving 50-60 millimeter of rain, which of course was very welcome. But of course, if this forecast was still be there one day later when we arrived in Madrid, it was not quite clear, so we spent one day trying to find out which of these forecasts is the correct one. And applying group velocity thinking, we traced the change in the initial conditions to somewhere in the borderland between Mexico and the southern USA. And analyzing the observations and the history, we found that the later forecast probably was more correct than the previous one. And so it turned out, and when we came to Madrid, we were told, we came early in the morning, we were told that the later forecast had confirmed the previous one, so rain was now almost certain to fall, and it did so. And here is a summary of the energy or the error propagation that we found when the flow was rather zonal from west to east. In winter time, the arrows moved along this line, so when there was a forecast failure on day 3 over Europe, it mainly came from eastern North America. A forecast failure on day 5 over Europe mainly came from western USA or easternmost Pacific. And there were even occasions when we traced arrows back 7 days, a 7-day forecast. The arrow came from somewhere over the western Pacific. And in the summertime, when you have a sort of subtropical high over the lower latitudes, the arrows move in a slightly northerly path over Canada. And that is important because there are less observations over Canada than over America. So also in summer times there were cases of downstream development of arrows from Canada. Then a joker in the game in late summer, in autumn, were occasions of tropical storms coming from the tropics and entering into the westerlies. And since they were very rich of energy and not always perfectly analyzed, they were also a cause of severe forecast failures. And all this could be discovered and understood by the group velocity thinking, how rapidly influences move in the atmosphere. Then in the US in particular, group velocity thinking has also been used to improve the forecast. So if we know where the errors come from, then we can also know where to put extra observations to improve the forecast. And what is used for that is mainly drop zones, where you fly and you drop down. Instead of having balloons going up with instruments, here you have parachutes coming down with instruments. And here is a case I got from America, from Zoltán Tóth, and it shows a 4-day forecast. A 4-day forecast over the United States, and here you have a 500 hectopascal trough, and underneath you have one of these awful northeast storms, east coast storms, hitting Washington, Boston, and New York. And they are very important to forecast because these areas are very populated, and also that's where the money comes from. So they have to be happy with the forecast. Now it's a question, this is a 4-day forecast. The next forecast will be a 3-day forecast. Now how can we improve that 3-day forecast? Where should we put extra observations? And with this group velocity thinking, both subjectively and mathematically, they are able to identify that in the initial conditions they should put extra observations in this trough far out in the Pacific to improve the 3-day forecast of this storm. But then the question is of course, are we looking at the same system? This trough, will that 3 days later be this trough? Are we talking about the same system? And the answer is no. We are actually dealing with two different systems. So the trough where we put extra observations into, it will move in the final just west of Canada. It will not even enter the American continent. It will stay out of the continent at least for the first 3 or 4 days. Whereas the storm that we wanted to improve on, already at the start, is halfway into the American continent. So we actually spend money to improve on a system that will hardly reach America, whereas this system is not in need of any new observations. It is still well analyzed. The point is that if we don't improve the analysis and the forecast of this system, the errors from this one will spread rapidly eastward and contaminate the storm that we are interested in. So this points to the, again, to the counterintuitive behavior of the atmosphere, but it's well described by the mathematics. We all have to understand the mathematics and to update our common sense of the behavior of the atmosphere. Thank you.